everyone, in this video I'll be covering section 2.8. 2.8 stems exactly from 2.7, so you should have watched the Professor Leonard video on 2.7. That video gets you the concept of calculating the slope at a specific point on a function, or you could say of the tangent line to a point on that function. The main concept is, let's say we have some big curve in our function. We have a point on that curve. Well, we know from section 2.1, you can't just find the slope of one point. You need 2 points to be able to find the slope. So the idea is, well, let's take these 2 points that are out here. Let's make them get closer. There's a little line between them, of course. Closer. There's a line between them. You can calculate the slope of the line. Closer, 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 closer until you're right on that point of the function. Once you're there, there's this teeny, teeny, tiny little line that you're calculating the slope of, and that line is so small and so close to that point, we say it's an exact approximation of the slope of that point. So that is actually the concept of a derivative. The derivative is the underlying concept of calculus. It's what we talk about through the entire course. That is why I was so adamant that we understand the reasoning behind the derivative. So in section 2.8, it's going to feel real similar to section 2.7, except for now we're putting this name, the derivative, in with what we were talking about in section 2.7. All right, so in section 2.7, you worked a lot with this equation. The limit as h goes to 0 of f of a plus h, or h plus a, either way is fine, minus f of a over h. All right, we found that this is the equation that we have when we're trying to find the slope of the tangent line to a point on some function. All right, this equation actually is representative of what we call the derivative. The only difference between this and the derivative is we name it the derivative a, and we can also represent the derivative as a function. So when we represent the derivative as a function, it just means you can plug anything into it. So in section 2.8, we might have said where a is 1 and put a 1 here and a 1 here, and then had to run that all the way through, and then maybe we had to do it with a 3 or a 5 or a 7. If we have this, the derivative, as a function, what we can do is calculate the derivative with this equation and then plug any number we want into it without having to recalculate every single time we want to find the slope at that point. All right, so let's get the exact definition in for a derivative and also get the notation that we'll be using in. So the derivative is the slope of a line tangent to a particular point. That should sound familiar. If we think of that regarding a specific point, we write f prime of a, so a is that specific point, that specific spot, is equal to the limit as h goes to 0 of f of, you could do h plus a or a plus h, that part doesn't really matter, h plus a minus f of a over h. Right, so the things to note here is, number 1, I'm using some different notation. That's because I'm now calling this a derivative. So this little tick here, we call it prime, okay? This denotes the derivative. It means you're taking the derivative. Denotes the derivative, okay? And it's said as f prime, it's called prime of a. All right, so that little thing tells you you're taking the derivative. We have f prime of a. Okay, here a is just some point. So I'll say where x is equal to a. So that's some specific point in terms of calculations. It would mean you're plugging an actual number in for a and then running through all of your calculations. All right, like I already said, sometimes it's a little bit inefficient to do this. Maybe we don't want to run 10 different numbers through one function. Maybe we want to just have the function, make it shorter, and then run it through. So obviously this limit function is really long. You've worked with it. You've seen that it takes a lot of algebra. If at all possible, I'm sure we would all prefer to avoid that algebra where we can. So thinking about the derivative as a function is what allows us to avoid doing this algebra every single time we do a calculation. So if we want to think about this as a function, we can say f prime of x, or whatever your independent variable is, maybe you call it t or w, doesn't matter, but that's your independent variable, is equivalent to the limit as h goes to 0 of f of, and you could write h plus x or x plus h, whatever you want is fine. I'm going to do h plus x because I think that's just more normal. I don't know. Okay, minus f of x over h. So here, the x is your independent variable. So where x is your independent variable. Okay, all that's saying is, all right, well, if you have x here, then you can plug, once you run through this whole derivative, through this whole entire equation and simplify, you can plug any defined number in for x. All right, and I have the question, why a function down here? So if we were in class, I'd say, now, why would we want to make this a function again? And I would hope your response would be, so we can make things more efficient. So really, it's for efficiency. Okay, another thing is it also helps to see where our derivative is defined. That really means where this function is differentiable. So it also helps to see where the derivative is defined. All right, a little bit more vocab here. That just means where the function is differentiable. Where the function is differentiable. All right, so where the derivative is defined, we say it's differentiable. If we have a space where the derivative is not defined, then we would say it's not differentiable. So sometimes having the shortened derivative function helps you see like, wait a second, I can't divide by 0 here, or I can't take the negative of underneath the square root, etc. It gives you a concept of where it's differentiable by looking at it analytically. So in the next examples, I'll show you what I mean by that. All right, so let's tackle this computationally first. So example 1 says, consider f of x equals x squared minus 12x. Calculate f prime of x, that just means the derivative, by using the definition of the derivative. Okay, so first thing to note here, if this specifies by using the definition of derivative, it means that we must use the limit as h goes to 0 of x plus h minus f of x over h. The reason I specify this is there are derivative shortcuts. We'll absolutely get to them, but we start with this so we understand where all of those shortcuts come from. When I teach this class in person, there are always a couple of people who just use the shortcuts. When I do it online, it's even more prevalent, and that's because a lot of people, hopefully are watching now, but don't watch the videos or really pay attention to the notes and just Google things. So they start doing shortcuts, and some of them don't really know like why they're there, what they do. So if it says definition of a derivative, it means you absolutely must use the definition of a derivative. Therefore, we're going to do that. All right, so first thing we have to do is recognize, we have definition of a derivative. So f prime of x is the limit as h goes to 0 of, I already wrote this. So the first part of this is f of x plus h. All right, remember compositions of functions. If you don't remember this from algebra and pre-calc, you should look up compositions of function and review it. If I have f of x plus h, that just means plug x of h in wherever you see an independent variable in this original function. So here, I'll do this in color so you can kind of see what I'm doing. All right, so I'll do blue for the f of x plus h, blue. All right, so I need to plug x plus h in everywhere I see an x in this function. All right, so blue, I'd have x plus h squared, just plug that in where this x was, minus 12 times x plus h. All right, now I've run that through the whole function, so I'm done with the f of x plus h part. All right, next I need to have my little minus sign from my derivative equation. So this minus comes from here. Okay, and I need to look at f of x. Well, f of x is kind of nice because it's already spelled out for me. So f of x, I'll do green. Here it tells us exactly what f of x is, so all I have to do is substitute the x squared minus 12x in. All right, and then from our derivative equation, this is all divided by h. All right, so if you're looking at this and thinking, that's a lot of algebra, you are correct. So, oops, this should be extended out here. There we go. We do have a lot of algebra to do now. All right, misconception that I was seeing in last week's discussion where, if I run this limit as h goes to 0 through, that means it's undefined. No. It doesn't mean it's undefined. It doesn't mean the derivative does not exist. What it means is you need to try to do algebra to undo this h down here, to divide it out, to cancel it out, however you want to say that, so you can run your limit. So we need to go through a lot of algebra, see if we can take care of this h. If we can't, we have to use alternative methods, but it's going to work out nicely, so we don't have to worry about that. Okay, so, and when I say nicely, I just mean we can do algebra. Not that the algebra is going to be nice necessarily. Okay, so running through the algebra, definitely going to have to simplify the numerator here. I'm going to start by FOILing out the x plus h squared. When I do that, I'd get x squared plus 2xh plus h squared. Right, that's going to be minus, now I need to distribute this negative 12 through both terms in the parentheses. So we have a minus 12x minus 12h. Next, I'll distribute this negative, so we'd have a minus x squared, and then minus a negative gives us a plus 12x, right? That's all still over h. All right, continuing on with that numerator simplification, I see the x squared subtract out to 0. So the x squared subtract to 0. All right, we have the negative 12x and the plus 12x subtracting out to 0. Okay, and now we're left with 3 terms that are not like terms, so we can do no more subtracting out, which means on the numerator we're left with h squared plus 2xh minus 12h over h, and I look at that and I'm really happy because I see that I can certainly, I can certainly factor an h out of the numerator, which allows me to undo that problematic h in the denominator. So I have the limit as h goes to 0 of h times h plus 2x minus 12 all over h, and dividing the h's out, I see that I now have the limit as h goes to 0 of h plus 2x minus 12. This is fantastic because I see now if I run my limit, I get something that's defined, meaning I get a clearly defined derivative function. All right, so since h is going to 0, I know this goes to 0. Okay, when I have 2x, that's not impacted by the h at all. If h goes to 0, it doesn't change what x does, so I know I still have the 2x, and negative 12 is just a constant. The limit of any constant is itself, so we know that we have minus 12. Therefore, we can see the derivative is 2x minus 12. All right, now thinking about, well, where is this differentiable? Okay, this is a polynomial function. So remember from the previous notes, polynomial functions are defined everywhere. Therefore, we know this f prime of x, I'll say the derivative f prime of x is a polynomial function. Okay, therefore, okay, this function f is differentiable, meaning you can take the derivative everywhere. All right, so now if I were to ask you, oh, what's f prime of 1? What's f prime of negative 10? What's f prime of 1,000,000? All you would have to do is just plug those numbers into this function. You'd be done. You wouldn't have to run through this entire stream of algebra that we just did. So it's really convenient to just get it as a function so you don't have to run through the algebra every single time. All right, next example, we're considering f of x equals 1 over x squared. We want to calculate f prime of x by using the definition of a derivative. So again, I know when it says definition of a derivative, I need to use the limit as h goes to 0 of f of x plus h minus f of x all over h. All right, so let's run that through this function. When we do so, we denote the derivative, aka f prime of x. We know we have the limit as h goes to 0. Again, I'll do the f of x plus h part in blue and bracket it out so you can see what I'm doing there. All right, so my original function is a fraction, so I have 1 over. I see an x squared. I need to run the x plus h through that x squared part. So I have 1 over x plus h in parentheses squared. All right, now I need to carry through with my minus from the derivative function. So this minus sign here, I have here. Okay, so minus. Right, now I'll do f of x in green. So again, this one's nice because it's just given to us right here. F of x is 1 over x squared. So I'll just write 1 over x squared. Right, and now I need to carry through with the last part of the derivative function, and that is, this is all over h. All right, so here we've done the derivative notation part. Now what we're gonna do all stems from section 2.3. So it's all about just doing that algebra to undo the h because I know I can't run my limit right now. From 2.3, you should remember, oftentimes if I see two fractions in the numerator separated, and I know I have to do some cancellations, some simplifications is a better way to say that, we probably have to combine those fractions by finding a common denominator. That's exactly what I'm going to do. So the next thing I'm going to do is find a common denominator between the two fractions in my numerator. All right, so when I do that, I get x squared for the first one. So notice in this denominator, I don't have just an x squared multiple, it's all squared, so I can't just like boil that out or anything, not yet anyway. So this is going to be x squared in the numerator minus, this minus sign comes from here, and I need an x plus h all squared in the numerator here, again, because x plus h all squared is not in this denominator, so I have to get a multiple of it, right? And then that is all divided by the common denominator of x squared times x plus h all squared. Right, we have this h in the denominator, but we learned in 2.3 that we can just write this as times 1 over h. So I'm going to do that just to save myself from writing a fraction over a fraction, but it all means the same thing. Okay, so now we have some simplification to do. So I have the limit as h goes to 0. I'm definitely going to need to FOIL out that x plus h all squared. So I have x squared minus x squared plus 2xh plus h squared all over my common denominator of x squared times x plus h squared, all that multiplied by 1 over h. Right here, I'm going to distribute my negative, and I'm also going to do my subtraction at the same time just to save some steps because I'm running out of space here. Okay, so x squared minus x squared is 0. Those terms zero out. Right, then I have a negative 2xh because I have to distribute that negative through. Okay, plus a negative, so really, well, okay, so negative times a positive gives me a negative, so I'll just say minus h squared, that's easier to do. Okay, all over x squared times x plus h all squared times 1 over h. This is fantastic because I can see in the numerator, I can factor out the h to divide out with this h, which means I am now, after I do that, going to be able to run my limit. So I have h times negative 2x minus h all over x squared times x plus h all squared times 1 over h, right? My h's divide out to 1 here, so did what I set out to do. And I can see once those divide out, I can run my limit. So I'm just going to do that with this first fraction. All right, again, we know that the h going to 0 does not impact this x at all. So I still have the negative 2x in the numerator. However, this h will go to 0 because h is going to 0. Right? Similarly, in the denominator, h going to 0 doesn't impact this x squared, so I simply rewrite it. Okay, same thing in these parentheses, but I see this goes to 0, so I really just have x squared. Right, let's simplify that to make it nicer. So I have negative 2x over x to the 4th, which is the same as negative 2 over x cubed, and that gives me my derivative function. So f prime of x we found to be negative 2 over x cubed. And then these little lines just mean I'm done. So I just use that to denote that I'm done taking that derivative or with that question. All right, so next part of this says use your result from A to calculate f prime of 2 if possible. All right, well, this is really nice. We have the equation for f prime, which means we don't have to go through all that algebra. We can simply plug 2 into f prime of x. Therefore, we have f prime of 2 is equal to negative 2 over 2 cubed, which is negative 2 over 8. And that is equivalent to negative 1/4. All right, so what this means in words is that the derivative at x equals 2 is equivalent to negative 1/4. Okay, it's defined, it's there, we're good. All right, now let's do another one. Use your result from A to calculate f prime of 0 if possible. All right, so, all right, I have f prime of 0. That's equal to negative 2 over 0 cubed. Ah, this is a problem, okay? So this is undefined. Okay, what this means is that this function is not differentiable at x equals 0. So this tells us it's not differentiable at x equals 0. All right, let's do one more analytical example, one more computational example, and then we'll move on to looking at this graphically. All right, so next we have f of x equals the square root of x. We want to calculate f prime, the derivative, by using the definition of the derivative. So remember, this means that we have to use the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, first thing that I'm going to have to do is run this through my function. So we have f prime of x is equivalent to, I'm going to run my x plus h through, I'll color that in blue. So we have the square root of x plus h, just ran that through here, so plugged x plus h in for x, hold the minus sign from our derivative definition, so that's this minus sign. Now we run the f of x through, aka just substitute it in because f of x is already given to us, so we have minus root x. Right, and then we have that over h because, again, that's what the definition of a derivative said, and you should have noticed I missed something really big here. So if you were to do this, I would say, your notation. Hopefully you'd notice like I have those. So here, we can't forget that limit. We have to run it. It's essential that I actually write the limit in here. So said it verbally, didn't write it. I need to write that in there. All right, from here, this should look exactly like a 2.3 question. You should see, I have a square root plus or minus something. This means I probably have to multiply by the conjugate. So we did this several times in section 2.3. Let's go ahead and see if that helps us run this limit. We clearly can't run it right now because we'd have something undefined in the denominator. So let's multiply by the conjugate. That is x plus h minus plus root x over root x plus h plus root x. All right, remember that we have to use this fraction here because really it's equivalent to 1. So all we're really doing is changing the way we're writing this. But if you multiply something by 1, it doesn't completely change the expression. It means you're still working with the same thing. So it's vital that you use a fraction when doing this for that reason. All right, so let's run through this multiplication. If we do, we'd get an x plus h. Okay, that's multiplying the first term is multiplying the outside. We'd get root x times root x plus h, the inside minus root x times root x plus h, so those subtract out to 0. Then we have a minus root x times positive root x, so that's minus an x, so the roots undo themselves there. All right, so that's our multiplication, and now we have h from right here, and I'm just going to rewrite this conjugate. So root x plus h plus root x. Okay, this is equivalent to the limit as h goes to 0 of the x's subtract out of the numerator. So we have h over h times root x plus h plus root x. All right, the h's divide out here, which is fantastic because that's what we wanted to happen. So we're left with the limit as h goes to 0 of 1 over root x plus h plus root x. At this point, I can absolutely run my limit, so let's go ahead and do it. Right here, the limit, we have the limit as h goes to 0. So this h goes to 0, which means we're left with 1 over root x. All right, for this plus root x, doesn't impact that root x at all, so we have a plus root x, right? Combining like terms, that's really 1 over 2 root x, so we can just add those together, and that is my fully simplified derivative. So I see that f prime of x is equivalent to 1 over 2 times root x. Okay, so that would be my final answer. All right, now following up with that, says use your result from A to calculate f prime of 16 if possible. All right, let's see if it's possible. So we have f prime of 16 is equivalent to 1 over 2 times root 16. That is 1 over 2 times 4. Therefore, we have 1 over 8. We can see that's absolutely possible. We were able to run it through. Good to go. All right. C says, use your result from A to calculate f prime of negative 4 if possible. All right, let's do it. So f prime of negative 4 equals 1 over 2 times root negative 4. Okay, this is a problem, right? It's not defined here. Undefined, you cannot have that square root under a negative, at least not in a regular Cartesian plane. You could in an imaginary coordinate system, but we're not working with those right now. So it's undefined for our purposes, which means that it's not differentiable at x is negative 4. And really, if we're being more specific, we could say it's not differentiable for any x as less than 0. And if you think about that logically, this function is a square root function. Okay, remember square root functions look like this graphically. So there's not even a function over there anyway. So that makes complete sense, because how are you going to take the derivative of something that's not even there? It doesn't make sense. So we should get that that's undefined and not differentiable at a place where the function doesn't even exist. Okay, so hopefully in the examples we have above, we got a good concept of how to determine if something was differentiable when we're looking at analytical computations. We are going to want to look at this graphically as well. That helps us get a full picture. So if we use the definition of a derivative to calculate a derivative function, we know the original function is differentiable where the derivative is defined. Okay, so that's computationally speaking. What we're going to do is extend this to the graphing, the graphical, the visual concept, so we can kind of think about, what this looks like. So in my next video, I'll show you what that looks like. We'll look at derivatives graphically, and we need to introduce a few things before we talk about when it's not differentiable, but we will definitely work on that concept. Okay.